Hello everyone and welcome back. My name is Mr. Cobalt, and in this video what I'm going to show you today is how to predict whether a redox reaction is going to be spontaneous or not, and how to sketch the electrochemical cells for the proper reaction. So we're going to do two examples. The first example is this redox reaction here. So we got solid iron reacting with the metal 2 plus, magnesium 2 plus aqueous, and that's going to transfer electrons from the iron to the magnesium. So then the iron becomes 2 plus and the magnesium becomes a solid. So is this going to be spontaneous or not? So the first thing you need to do is write the potential half reactions, the redox reaction. So you got to write down what's reduced, what's oxidized, and then look at the reduction potentials, standard reduction potentials for the electrodes. Okay, so I have here written down already the half reaction. So we have iron solid going to iron 2 plus. So that's going to lose 2 electrons. So it's undergoing oxidation. And then we got magnesium going from magnesium 2 plus to magnesium solid. So that's going to gain 2 electrons. So that's going to undergo reduction. So here we have the oxidation reaction, and here we have the reduction reaction. And here we have the electrode potentials. Now remember, the electrode potentials are written in for the reduction half reactions. So it's important to keep in mind that the more negative the reduction half reaction, the reduction potential half reaction, or electrode potential, it means that it's going to be more likely to repel the electrons at that electrode. Okay, so think about negative. The more negative the electrode potential, the more likely it's going to repel electrons, because electrons are negative, right? So think about negatives. Negatives repel each other, like charges repel each other. So the more negative your electrode potential for reduction, the less likely that electrode will attract electrons. So it's not going to go towards that electrode, it's going to go away from those electrodes. So this is going to help us figure out which direction the electron flow is going to happen for our electrochemical cell. Okay, so here what you notice is that for this reduction half reaction, the standard electrode potential is negative 2.37, and for the reduction half reaction for iron 2 plus, it would be written in this direction. That is negative 0.45 volts. So since this is more negative than this one, since the reduction half reaction electrode potential is more negative than this one, then we would expect that it would be more likely that the electrons would be attracted to this electrode than to this electrode. So think about the more negative you have, the higher potential energy the electrons have at that electrode, and the more positive or less negative the standard electrode reduction potential, the lower the energy, the lower the potential energy. So electrons are more spontaneously going to go from high energy to low. So you can think of it that way. Another way is that electrons being negative are going to move away from the more negative electrode potential to the less electronegative, or less negative, or more positive. So, so here you have more negative. So it's more likely that the electrons are going to move away from this electrode. So instead of magnesium 2 plus picking up 2 electrons and moving towards magnesium solid, it's more likely that it's going to be oxidized instead of reduced. So magnesium is more likely to be oxidized than it is to that magnesium 2 plus is to be reduced. So this would go in the backwards direction. So the way this is written right now is not spontaneous. So the way it's written is that the electrons are going to be picked up by magnesium 2 plus, and so this would be reduced to magnesium solid. But because the electrode potential here is more negative, that's not likely to happen. It's more likely it's going to go in the reverse direction, and this one is actually going to be reduced. So we need to flip these around. So the way this would actually work would be in the opposite direction, where magnesium is going to be giving off electrons to iron 2 plus. So it's going to be spontaneous in this direction, but not spontaneous in the direction. So the way it's written, it is not spontaneous. So let's draw an electrochemical cell to what's the word I'm looking for? To sketch or represent or show what the flow of electrons will look like in this A here. So give me a moment. Okay, so as you can see here, I have sketched out what the electrochemical cell is going to look like. So I rewrote here the reactions we have, but remember, because this reaction, the reduction reaction, is more negative than, or the electrode potential for the reduction half reaction is more negative for the magnesium plus 2 plus ion than it is for the iron 2 plus ion, then that means that the electrons are going to be repelled by this electrode here than this one. So they're going to move away rather than being picked up by magnesium 2 plus to form magnesium solid. Magnesium solid is more likely to be oxidized. So it's not going to move in this direction, it's going to move in this direction. And the same thing with the iron. So what does that mean for the sketch of our electrochemical cell? So we got to pick a cathode and anode side. So remember, at the anode, oxidation is occurring. So we know what we said before is that the reaction is actually going to go in this direction. So that means, again, because this is negative, this is actually going to be oxidized, right? So it's going to be moving in this direction. So oxidation is going to happen at the anode. So that means we're going to need our anode to be made out of magnesium. So that's going to be a magnesium anode or electrode. And we're going to need some salt solution here, or we're going to need an aqueous solution of magnesium 2 plus ions. So we're going to have magnesium 2 plus aqueous solution there. And on this side, this is going to be our cathode. So this here, the reaction is going to go in that direction. So magnesium is going to give off the electrons, remember? So the electrons are going to move away from the more negative electrode potential to the more positive electrode potential. So it's going to go from the magnesium to the iron 2 plus. So then that means iron 2 plus, and we're going to go back this way. Iron 2 plus is going to form iron. So we're going to have an iron electrode there. So reduction is going to happen here. So iron 2 plus is going to be reduced. It's going to gain 2 electrons and form the iron. Magnesium is going to lose the 2 electrons and it's going to form magnesium 2 plus. So the electrons are going to be flowing in this direction here. So magnesium is going to lose the 2 electrons, and so more iron So magnesium is going to be more magnesium 2 plus is going to be formed from magnesium. So because it's losing those electrons are going to be picked up by the iron, the solid iron, and then the solid iron is going to, oops, my bad, the iron ions, right? So you have these iron 2 plus ions. Those iron 2 plus ions are going to pick up the electrons and they're going to make more solid iron. So over time, what you should expect to see is that this electrode is going to get larger and larger and larger. You're going to build up on that. And then this electrode is going to get smaller and smaller. It's going to corrode and lose mass. And so that's your electrode or your electrochemical cell and how you would sketch it. And then of course you have your salt bridge here. And the purpose of the salt bridge is to keep the system going longer. So the reason is because as you put more and more ions, positive ions in here, right? This is going to become more and more positive. This is as more ions leave the solution, this is going to become less and less positive. And so to keep that going, so you need some negative and positive ions in here that can flow to counterbalance the growing positive here and the growing negative or less positive there. So, because otherwise, what's going to happen is eventually the electron flow is going to change. It's going to slow down because this becomes more positive. This becomes less positive over time. Okay, so what about B? Let's go ahead and do B. So if we do B, so let's erase this. If we let's see here. Okay, so now we're gonna look at this one here. So this one here is basically the same, except we are using iron. So if we write the half reactions here, so iron solid again is going to go to iron 2 plus 2 electrons. And then now here what we have is lead here, lead 2 plus 2 electrons is going to go to, oops, is going to go to lead solid. And if we look up the electrode potentials for lead, so lead is going to have a negative 0.13. So this is a negative 0.13 volts, and then again this is a negative 0.45 volts. And so what you can see here is this is going into oxidation. Oxidation is lost. So here we have iron being oxidized again, and here we have lead being reduced. But now you'll see that the reduction potential, the electrode potential of this reduction half reaction is less negative than this one. So in fact, the electrons are going to be repelled by this electrode and attracted to this one. So this one is less likely to undergo reduction, but is more likely to undergo oxidation spontaneously, and this one's going to undergo reduction spontaneously. So the electrons will move from iron to lead. in a spontaneous direction. So this is a spontaneous